Suppose I give you a weighted graph and ask you to split its node into two groups. For this tiny graph, maybe I separate node C from A and B with the cut cost of -5, which is the sum of the weights of the edges that are cut. But that is just one possibility. There are also other ways to split the graph, and each gives a different total cut value. The goal of MaxCut is to find the split that has the largest possible cut value. For a graph with 3 nodes, this is easy. You can almost do it by inspection. Once the graph has, say, 10 nodes, 20 nodes, or 50 nodes, the number of possible partitions grows explosively, and that is exactly why MaxCut is such a famous problem in computer science. It is one of the classic NP-hard problems, which means that finding the exact best solution becomes extremely difficult as the problem size grows. Given the fact that you're watching this video, the natural question should be, can we rewrite this problem in a form that is friendly to quantum optimization methods? And that brings us to QUBO. First, let's take a very brief look at the different types of optimization and see where QUBO fits into the bigger picture. Broadly speaking, optimization problems can be divided into two main types: continuous and discrete. In continuous optimization, the variable we are trying to optimize can take any real value. On the other hand, in discrete optimization, the solution space is not continuous and the optimization variable can only take certain allowed values. Continuous optimization can be either convex or non-convex. For those of you coming from a machine learning background, the loss function is a good example of a continuous optimization problem. In the convex case, a standard example is linear regression with mean squared error as the loss function. The landscape of the function to be optimized looks like this. Problems like these are considered relatively easy because any local minimum is also guaranteed to be the global minimum, which makes them efficient to solve. Then there is the non-convex case. A common example here is the loss function of a neural network, where nonlinear activation functions in the hidden layers make the optimization landscape much more complicated. Non-convex optimization problems are definitely harder, but since the landscape is still continuous, we can often make useful progress using gradient-based methods. In other words, many continuous optimization problems, especially in machine learning, are differentiable and mathematically considered well-behaved, which is why methods like gradient descent become useful. The key difference between continuous and discrete optimization is this. In continuous optimization, a small change in the input variable usually leads to a small change in the value of the function. In contrast, for discrete optimization, there is no real notion of a small change. A change in the input variable can lead to a significant change in the value of the objective function. Now, once we enter the world of discrete optimization, many practically relevant problems turn out to be combinatorial. That means the number of possible solutions can grow exponentially with the size of the problem. You may also come across other categories in some sources, such as integer programming, where the variables can take only integer values, but it is just a mathematical framework to model combinatorial problems. In general, combinatorial optimization problems are hard to solve exactly at scale on classical computers. In the worst case, many of them are NP-hard, so in practice, we often rely on heuristics, approximations, or relaxations of the original problem. And these are not just abstract textbook problems. Everyday applications include logistics, supply chain optimization, airline network planning, optimal task allocation, or even finding efficient delivery routes for your packages. In many of these cases, classical methods are used to find solutions that are only near optimal. And while near optimal solutions are often good enough in many practical scenarios like these, there are certain critical areas such as drug discovery or material science where a near optimal solution may simply not be sufficient. Going one step further, combinatorial optimization problems can again be categorized into constrained and unconstrained problems. QUBO falls under the unconstrained optimization. We will explore how to formulate a constrained combinatorial optimization problem as a QUBO in later videos, but for this video, let's stay focused on the unconstrained case, specifically QUBO. QUBO is one of the most important native formulations in quantum optimization, especially because it maps naturally to the Ising model, which is the energy model used in physics. So to summarize, discrete optimization is generally harder than continuous optimization. Many practically relevant discrete optimization problems are combinatorial, and QUBO belongs to this combinatorial optimization setting, specifically the unconstrained case. If all of this is overwhelming, the only key takeaway is that QUBO is a hard problem, and let's delve into understanding it better. Let us start this section with such an abstraction where a QUBO solver takes in an input and provides an output. In general, for any solver, typically the input is a problem and the output is a solution. In case of QUBO, the problem is a symmetric matrix conventionally expressed by the letter Q, and the solution is a binary vector, or in other words, a binary column matrix expressed by the letter X. If the size of the matrix Q is n cross n, then the solution X is a binary column matrix of size n cross 1. And the task of the QUBO solver is to find the optimal binary vector X, which provides the least value for this expression, that is the product of X transpose, the symmetric matrix, and again the column matrix X. Let's check the dimensions of these factors in this expression. Operating from right to left, we first multiply Q and X, which will obtain the product QX having a dimension of n cross 1. Then further multiplying that with X transpose, we get a real value. So mathematically, a QUBO problem is expressed in this way, and the task of a QUBO solver is to find that X which minimizes this function. Remember the problem that we saw at the beginning of this video, the MaxCut problem? It can be solved as QUBO. So the idea is to formulate the input of the MaxCut problem, which is a weighted graph, as the symmetric matrix Q, then feed it to the QUBO solver to obtain the optimal solution X, which can then be decoded to the MaxCut solution. Since the graph here has 3 nodes, Q is a 3x3 symmetric matrix, and the solution is a binary column matrix of size 3. The question now is how to interpret these numerical values. Let's first focus on decoding the solution, which is very simple. The first binary value corresponds to the node A in the graph, the second corresponds to B, and the third corresponds to C. All those nodes that are assigned with 0 are separated from those nodes that are assigned with 1. In this case, A is separated from B and C with a cut cost of 6, which is the sum of the weights of the edges AB and AC which are cut. Now let's shift our focus on how to obtain the matrix Q given the weighted graph. Here the first row and the first column corresponds to node A. Similarly for B with the second row and the second column, and the third row and the third column corresponds to C. Let's see this non-diagonal element here, which is 8. It is the element of the row corresponding to A and the column corresponding to B. The value 8 is the weight of the edge that is connecting A and B. This is also the element same as the row corresponding to B and the column corresponding to A. Applying the same strategy, we obtain all the upper triangular elements and the lower triangular elements, basically all the non-diagonal elements, because it is a symmetric matrix, and these non-diagonal elements are called as quadratic coefficients. And there are also diagonal elements. Let's first see how we got this diagonal element here. It is in the row and the column corresponding to node A, and the value -6 is the negation of the sum of the weights of the edges that are connected to the node A. Similarly, we obtain the second diagonal element corresponding to node B and the third diagonal element corresponding to node C. These constitute the diagonal elements, which are termed as linear coefficients. Now let us understand why these non-diagonal elements are called as quadratic coefficients and these diagonal elements are called as linear coefficients. Initially, the QUBO solver obviously does not know the solution. It solves this minimization problem to find the X. X here is a binary column matrix of size 3. Since we do not know the binary values before solving, we denote the components of X as binary variables x1, x2, and x3, and Q is this input matrix. Now let us consider this expression. Start with substituting the values of X and Q, then continue further with multiplying the matrices. For matrix multiplication, we go from right to left. So first multiply Q and X to obtain a column matrix like this. Going ahead with multiplying the row matrix with the column matrix provides this expression. Multiplying the terms inside, then we get this. Here we can further simplify by combining the terms with the same two binary variables. For example, this term here, 8x1 x2, can be combined with the term 8x2 x1 because x1 x2 is equivalent to x2 x1. So combining the appropriate terms will give us this expression. At this point, it is important to remember that the variables x1, x2 and x3 are binary, which means that they can only be either 0 or 1. This implies that the expression can be further simplified by just ignoring the squares for the binary variables, because 0 squared is 0 and 1 squared is 1. Finally, we end up at this expression. Coming back here, we can replace this matrix form with the expanded and simplified expression, and the task of the QUBO solver is to find the optimal assignment of zeros and ones to x1, x2 and x3 that gives the least value for this expression. Notice here the linear terms in the simplified expression. In other words, these terms with just a single binary variable. The coefficients of these terms are exactly the diagonal elements. Remember that x1, x2 and x3 corresponds to node A, B and C. Also keep in mind the positions of the elements in the matrix correspond to the nodes in the graph. So the coefficient of x1, which is -6, is the first diagonal element, which is the element in the row and the column corresponding to node A. Similarly, the coefficient of the linear term in x2 is -5, which is the diagonal element corresponding to the node B. And finally, the coefficient of linear term in x3 is +5, which is the diagonal element corresponding to node C. Since these diagonal elements are the coefficients of the linear terms, they are called as linear coefficients. Similarly, with the quadratic terms, I mean those terms which are having two binary variables highlighted here. Check this first quadratic term in x1 and x2. x1 corresponds to A and x2 corresponds to B, and the half of 16 is 8, which is placed in this position. We know that the QUBO matrix is symmetric, or in other words, since x1, x2 is equivalent to x2, x1, the same applies to this element in the row corresponding to B and the column corresponding to A. The same logic applies to this term in x1, x3 and this term in x2, x3. So the point here is, all these non-diagonal elements are derived from the coefficients of quadratic terms, hence they are called as quadratic coefficients. So to recap what we saw till now, given the weighted graph, we first derived the QUBO matrix from the graph specifically for the MaxCut problem. In fact, we are able to derive the QUBO matrix directly from the graph with the process we saw earlier only because we are considering the MaxCut problem. We then substituted this matrix in the QUBO expression and simplified it to get this. So the expression we have here, we actually obtained it from the QUBO matrix. And this was just to understand why the non-diagonal elements are called quadratic coefficients and the diagonal elements are called as linear coefficients. So if you are given this expression, you should be comfortable now to compose the QUBO matrix by identifying the linear and quadratic coefficients. In fact, this expression and the matrix are just two ways of expressing a QUBO problem. In general, given a combinatorial optimization problem, understanding the objective of the problem, we derive an expression in this form. Such an expression with linear and quadratic terms help in deriving the QUBO matrix. Let's see how we do it for the same MaxCut problem. As we saw at the beginning of the video, given the graph, we cut, or in other words, remove certain edges that will split the set of nodes into two mutually exclusive subsets. We can observe that the cut edges are actually the edges that are connecting the nodes from one subset to the nodes in the other subset. And the optimization objective of MaxCut is to maximize the sum of the weights of the cut edges. Mathematically, we can write it like this. Here, n is the number of nodes, which is 3, I and j are the variables for iterating over all nodes, and wij is the weight of the edge connecting the nodes xi and xj. Notice that this is a maximization problem. We can convert it into a minimization problem by negating the term inside. So expanding this iterative summation over all nodes, we get this expression. Further simplifying it, we obtain this. This expression is in the same form as what we saw before. There are linear terms and there are quadratic terms. Now we know how to formulate the QUBO matrix using the coefficients in these terms. Then the next step is to input this into the QUBO solver and get the binary column matrix. We know that the task of the QUBO solver is to find the optimal combination of zeros and ones for x1, x2 and x3. Hence, QUBO comes under combinatorial optimization and the number of possible combinations scale exponentially. And the only way to find the optimal solution is by brute force, and it is infeasible as the size of the graph increases. Let's get into the code to check this out. This is a Jupyter notebook available in a GitHub repository. The link is in the description. Clone the repo and run it locally, or you can run it also directly on GitHub Codespaces. I have cloned it locally and I shall give you a quick walkthrough of this notebook. I am running this on VS Code. You can use any IDE like Jupyter Lab if you are comfortable with it. So here there are some markdown cells which contain the theory about QUBO that we covered. We start with the abstraction of a QUBO solver that takes a symmetric matrix Q as input and provides a binary column matrix as output encoding the solution. Then we have the matrix representation of a QUBO problem and then expanding the matrix form and simplifying to get the expression with linear and quadratic terms. Now we get into formulating the MaxCut as QUBO. There are some libraries that are required to run this notebook. I have already installed it. As a good practice, I have created a virtual environment, enabled it as the kernel for this notebook, and have installed these dependencies. Just uncomment the lines in this cell and execute it to install these dependencies. After installing, we import them in this cell. In the next cell, we generate a graph using NetworkX library. In fact, the exact graph example we considered before for the MaxCut problem. Here, we are just plotting the graph to visualize it. Again, to repeat the objective, given this connected undirected weighted graph, the goal is to split the graph. Basically, the set of vertices are split into two mutually exclusive subsets by cutting the edges such that the sum of the edges that are cut is maximum. Now we proceed with formulating the QUBO matrix for the MaxCut problem. First, we get the adjacency matrix of the graph. Adjacency matrix is a way to represent a weighted graph in a matrix form, where the elements are edge weights. Now here is the objective function of the MaxCut problem. The Wij here is an element from the adjacency matrix. We can easily convert this into minimization by negating the term inside the summation. Substituting the terms and expanding the summation over all edges, we get this expression. Further simplifying fetches this expression. So this has linear terms and quadratic terms, same as this form, which is nothing but another way to represent a QUBO problem, and we know how to extract the coefficients from this equation to formulate the QUBO matrix. All the steps to get this QUBO matrix from the graph uses SymPy, which is a library for doing algebraic operations just like how we work this out on a paper manually. But SymPy is very slow for large expressions. Just because the MaxCut problem's objective function naturally has a QUBO form, we can extract the QUBO matrix from the edge weights in the graph directly as we saw before. This avoids using SymPy and it is more efficient for large problems. Let's now solve this QUBO problem to find the MaxCut by exhaustively enumerating all possible solutions and then choosing the optimal one. In other words, brute force. So we try all possible combinations of assigning 0 and 1 to the variables x1, x2 and x3. As we are minimizing this function, and we see that 011 or 100 has the least cost. Either of these assignments mean that x1 is separated from x2 and x3. In the graph we considered, this maps to separating node A from nodes B and C. And that is exactly what we are visualizing here, where the red colored edges represent the cut edges. Now that we have seen the example with 3 nodes that we have considered throughout this video, let's see if we can scale this approach. Here is a function to generate connected graphs with random edge weights given the number of nodes. There is also other default arguments like the range for choosing the random edge weights and a random seed for reproducibility. And we have defined the brute force approach to solve QUBO as a function, which takes the matrix Q as input and returns the optimal binary solution and its cost. Let us now execute this brute force approach for graphs with increasing the number of nodes up to 20. This way of brute forcing guarantees to find the optimal solution, so we can ignore the QUBO cost and assume it to be the optimal. But importantly, we track the time it takes for executing each problem. The execution speed usually depends on the hardware you are running it on, specifically the processor. Now that it is complete, let's plot the runtimes with the size of the graph. Irrespective of the machine you run this on, the runtime scales exponentially with the size of the problem, which is what we see here. This makes it infeasible for classical computers. Just observe the increase in runtime for solving a problem of size 19 and size 20, and you can try running it for a problem of size 25 and see it for yourself. There's also a better way to visualize such an exponential scaling by using logarithmic scale on the y-axis. Then it will look linear. With this, we can conclude, although we are guaranteed to find the optimal solution, brute force approach is an inefficient way to solve a QUBO problem, and it has a complexity of O of 2 power n and is considered infeasible for classical computers. Till now, we haven't talked anything about quantum computing. All these are classical computing concepts. In the next video, we will explore the behavior of the state-of-the-art solver QUBO, which uses a technique called branch and bound to find a near-optimal solution. More importantly, we'll explore how you can solve QUBO problems on a real quantum hardware by D-Wave, which you can access remotely.